Okay, this session, it's what, almost 4:30 p.m, starting to get a bit dark, so I put on my cap and switched on the light. Now in this session we're going to actually construct an equivalent DFA from a given NFA. And here's the NFA, the state diagram for an NFA, and in fact it's N4. Now you may remember from a few sessions back that I was predicting that we would use this particular NFA again, and well, now's the time. Now we actually use it. Okay, so it was N4 if you want to go back to earlier sessions and have a look at here. I've written it out again. Now the other thing that's different is the textbook has now put numbers instead of like Q1 or Q0, Q1, Q2 or something. Now it's just put numbers here. It's sort of easier to talk about, right? So what we have to do now is to construct the equivalent DFA for this NFA. That's the and we'll be doing that for almost two sessions. Right? So it's a lot of, as we get into it, there'll be a lot of details. So you'll need to concentrate. And there were a few surprises. Remember me saying that I'm still a bit fuzzy on the use of the eta, these eta arrows. And when I was going through this, I got some surprises. And I put like a triple exclamation mark on it. I'm wondering if you'll feel the same. Or did I miss something? Or did Sipser miss something? I still haven't quite figured that out yet. Hopefully by solving the problems in the problems section, the use of the eta arrows will become clearer in my mind, and I hope yours. Okay, right, so here's your state diagram for N4. That is the NFA that we will find a DFA that's equivalent to it. Okay, so this is what we start with. And we'll use formal description. So here's the formal description of this automaton, this NFA. Right? The usual. It's the alphabet is capital sigma. It's just binary, just two states, A and B. Okay. Start state is 1. You can just see that from the double circle. And it's also the accept state. Right? So the set of states that accept, there's only one of them, so you put set 1. Right? Now the set of states for this NFA. Now we're talking about the NFA for the moment, right? Not the DFA, just the NFA. We're getting started. Okay, so the set of states for this NFA is just obviously just 1, 2, 3. Just see that from so that's your capital Q. Set of states of your NFA, right? Okay, now we're going to try to construct an equivalent DFA, and we're going to label that just to make things simple and easy and to abbreviate things. We'll just call it capital D, right? So the equivalent DFA, this automaton that we will construct, that we will create, we'll just call it D, capital D. Right? So from now, it just makes things easier, because we'll be constantly referring to this equivalent DFA. That gets dull. So we'll just talk about D. It's easier. Okay. All right. So that's our NFA. This D will be our equivalent DFA. Okay. So let's find the states of D. Now remember from the theory and the proof, earlier proof, the states of an equivalent DFA of equivalent to some NFA, the states of that DFA are in fact the superset of the set of states of your NFA. In other words, Q. So the states of your, so in other words, the states of D, big D, is the superset of Q. Hope you follow that. Right? So D's states will just be the superset of Q. It will be the superset, sorry, not superset, power set. Sorry, power set. Okay. So the states of D will be the power set of Q. In other words, the power set of the elements 1, 2, 3 of that set. Okay. Well, and how many elements will that power set have? Well, you take the number of elements in your set Q, and you take that number, and that becomes the exponent. It's the power of 2 to whatever that number is. We have 3, so the number of elements in your power set will be 2 to the 3. In other words, 8. Okay, so we have 8 states. We'll have 8 states in our D, equivalent to this NFA here. Okay. Now, what are those states? Well, each state in D, the DFA, will be a set. Okay, so here they are. The null set. That's a subset of any set. Null set. And then a set with just one element. Well, there'll be 3 like that, with one element each. So 1, 2, and 3. And then the subsets with 2 elements. 2 of these 3 in it. Well, systematically 1, 2, 1, 3, 2, 3. All right. And the whole set itself is still a subset. It's an improper subset, but it's still a subset. Okay. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So there are the 8 states of your D, okay? The power set. So Q dashed is the power set. Follow me? Q dashed, the set of states in your D is the power set of Q. Right. Okay, and here they are. You're the 8. Right? Okay, so we found the states of big D. Now, how about the start state and the start with the starts. So what are the start state? Now remember that capital E function thing? We have to allow for the possibility that maybe the starting state in your NFA has eta arrows. So let's check. Here's the starting state, and there is an eta arrow. Right? There is one. Okay, so we need to use that capital E function that we did before, which adds states that the eta arrows point to. They add those states to the starting state. Well, starting state, obviously there's a 1 in there, so the starting state. So it'll be E of the members of your. It'll be E of this. Well, that will include the 1 itself and the state that it points to. So the starting state for your D will be the set containing 1 and 3. Why 3? Well, because there's an eta arrow pointing to it. That's the definition of this E. Okay? So the starting state of your D will be this. Right? That's your starting state, original one here, and this 3 comes, gets into this set because there's an eta arrow. Now, if you ask me a deeper question, why are you doing this kind of stuff? Why are you using these etas and so forth? That is less obvious to me. That hasn't clicked fully yet, and I don't think it will until I really start solving a lot of the problems in the problem session. no, maybe you do see why. Well, good luck. Anyway, all right. Okay, so that's the starting state for D. Okay. Now, how about what are the what's